Hi, everybody. This is Dr. Andrew Chrysler teaching EE3325 at Idaho State University. I want to take a minute and explain a few more steps on how we can use Gauss's law to find the electric field. So in class, we were looking at a problem that was like this. We had a set of charges, a line charge along the z-axis and a dark area that has a volumetric charge density. And we wanted to be able to find the electric field in a couple different areas. So let me explain some of the basic steps that you would take to solve a problem like this. And hopefully I can also explain how this could be applied to any problem that uses Gauss's law. So first, we want to see that this problem, right, is going to have a symmetry. And if we look, we can see that the electric field is going to be the same for all the way around this problem, halfway between this z-axis in the middle of the can. And so if we were to write generally the electric flux density for cylindrical coordinates, since this is in the cylindrical coordinate system, we would write that the electric flux density will take this form. And if we look at this, we can see that because of the symmetry condition that we have, there is going to be no electric flux density in the phi direction and no electric flux density in the z direction. So both of these are going to go away. So that means that our electric flux density is going to vary. It's going to be only valued in the r hat direction, and it's going to have some electric flux density dr. We don't know what dr is, but we should be able to figure this out. So this is the first step to do. If you're looking at a problem that was in spherical coordinates, right, we would start by considering the electric flux density, which could have a r direction, a phi direction, and a theta direction. And we would try to determine which one of these is also not changing. So perhaps if in the case where the charges were spherical shells, we would probably also have the case where these two are going to go away. Okay, so the first step is to consider a general electric flux density, determine which one of the directions that it is not going to be changing in, and find an expression for electric flux density that that we can solve for this value dr or whatever direction that you are working in. Okay, so once you've done that, the next step is to apply Gauss's law. Okay, and we can use the integral form of Gauss's law. So we'll apply the integral form of Gauss's law, which looks like this. And in our case, we saw that this was cylindrical. We had this direction. And so in the video in class, right, we saw that if we take this and substitute in what we determined, we will get r hat dr as our electric flux density, and then we need to dot this with some ds. Now, because of the Gaussian surface, we saw that the normal to the Gaussian surface, so the direction that we'll find the symmetry is going to be r. So we're going to use this as our r, so r dz d phi, and that is equal to q. I'm sorry. All right, so and then we need to solve this integral. So in our case, we go from 0 to L and from phi to 2 pi. So solving this side of the equation, the left-hand side, we can arrive at an expression for the magnitude of the electric field in the direction that we know it varies. So in this case, we are able to determine that this is equal to 2 pi RL dr on the left-hand side is equal to Q. So by solving the left-hand side of the equation, we can set it equal to the right-hand side, and then we can solve for dr, because we don't know what dr is. We don't know what the magnitude of the electric flux density is going to be. So we have dr is equal to Q over 2 pi RL. Okay. Now we have an expression for the magnitude of the electric flux density in the direction that we know it varies. And remember, we also know that d phi is 0 and dz is also 0. Right, so going back to this, and don't forget that our goal is to find the electric field, which is in air. All of these things are in air. So we can see, right, that we are very close to being able to find the electric field, because we now have an expression for the electric flux density and the magnitude of the electric flux density in the direction that we know it's changing, right? So and we found an expression for dr. And that was right here, that R equals Q over 2 pi RL. Just like this. So now we have an expression for the electric field, which is what we want to find, but we still don't know what Q is. So what is Q? And Q, remember, is on the right-hand side of our equation for Gauss's law, right? So Q is on the right-hand side of this equation. So we already solved the left-hand side, and now we just need to solve the right-hand side. Okay, so solving the right-hand side, means that we're going to need to find the total amount of charge. So remembering from some of the other homework problems, right, these are going to be, we're either going to have charges, single charges, line charges, surface charges, or volume charges. So those amount of charges are we're going to need to add it up. So if it's a line charge, right, we're going to get something, we're going to get a integral that looks like this so that we can find a total amount of charge in a line. Or we're going to need to do a surface charge integral to find the total amount of charge on a surface. Okay. Or we're going to have a volume charge, in which case we're going to need to do a volume integral to find the total charge on a volume, in a volume. Okay, and for each region that we're interested in, we need to sum up all of the charges contained in the total volume. Okay, so when we are inside of A, okay, so for part A, right, this part asks, what is the total amount of charge contained within this region? So all the way up to just before the shaded part. Okay, so all of the charge inside this region. Okay, and we know from the problem statement, right, that there is a line charge all the way along this axis. So for region A, for part A of this problem, right, the right-hand side to find Q is going to be a line integral to sum up all of the charges along the line that we're interested in. So the charges are in the z-axis from 0 to L in part A. And then in part B, we also need to find the right-hand side and find all of the charges in the region. So find all charges up to R is equal to B. So that is all the way out to here, and that includes the charges in this black shaded area, which had a volume charge density. So all of the charges in the blue area, so Q total is going to be equal to the charges on the line plus the charge in the volume. So we're going to need to find a Q that's equal to this, right? So the 0 to L, and you've already done this integral, plus all of the charges in that volume given by the volume charge density, right? And so that volume charge density is going to go from R is equal to A to B, up to B for the total charges, from 0 to 2 pi in the phi direction. Actually, sorry, this is going to be R all the way up to R, where R could be as large as B, and Z from 0 to L once again. If we wanted to find the charges, if we wanted to find the electric field for an area beyond B, okay, so let's call this C, not in the problem, but for R is greater than B, then we would need to find the total charge here. So we would change this from R to B, and this would give us the total charge in the total charge in that dark shaded semiconductor area. So we can find the total amount of charge by doing line integrals, surface integrals, or volume integrals. And the total amount of charge is then going to go into here. So we'll replace it into this variable, right? So these are the right-hand side. So we're going to solve these things, and these are going to be the right-hand side. So we can find the right-hand side for all of these different situations. So the further out we go, we can just continue to add up all of the charge, and we will get the equations, we will get expressions that tell us what the value of Q is, and then we can plug those in to Q. Okay, so for part A, right, we will take this expression for Q, and we will plug it in here so that we can get the electric field, right, to find electric field. And then for B, we will do the same thing. We'll use this expression that we determined. So we added up all of the charges inside that region by doing two different integrals. One was a line integral for the charges that are along the line, and one was a volume integral for the charges in that dark shaded volume. And we get another expression for Q, and we can just put that in here, and we can find the electric field for the region when R is greater than A, but it's still less than B. And if we were to go even further into an area that the problem didn't ask us about, we could add up all of the charges all the way up to B so that we could find the electric field inside of this area when R is even larger than B. So I hope that this helps you, and I hope you can see how this will, this method would be able to help you solve this for any type of Gaussian problem. Thank you.